Hey guys, we're going to do 3.8, so go ahead and try your warm-up, but you're just finding the first derivative of the functions. These are a little bit more difficult than just the basic derivative. We have some chain rule, quotient rule, stuff like that going on. All right, so number one, this one is going to be chain rule and also product rule. So we have, if you think of this as 7 plus x secant x to the 1/2. So we're going to have 1/2, keep the inside the same, put the 1/2 down to a negative 1/2. Now we have to do the derivative of the inside. So we're going to have product rule because it's x times secant of x. So we have derivative of the first, which is 1, times the second, plus derivative of the second, which is secant tan, times the first, which is x. I hope that didn't confuse you at all. I was never talking about the 7 when I was saying first and second, because the 7 is a constant, so the derivative is nothing. So when I was saying the first and the second, I'm really just talking about the x being the first and the secant x being the second.
Wow, that's weird.
Okay, number 2. This one is also chain rule. So we're going to bring the negative 1 down in front. We're going to keep the inside the same. Take the negative 1 down to a negative 2. Now we have to do the derivative of the inside, which is quotient rule. So we have derivative of the top. So it's going to be cosine of 3t times 3. The derivative of 3t is 3. Times the bottom. Minus derivative of the bottom, which is negative 2, times the top. Ugh, I'm out of room. All over the bottom squared.
Bottom squared.
Okay, number 3. Number 3 is chain rule. So we're going to start with the outside. So the outside is the secant. We have to do the derivative of secant first. So the derivative of secant is secant tan. Remember, we don't have an x inside of this secant. We have a tan x. So when we do our secant tan, we actually are doing tan x in each one of those trig functions. So we have secant of tan x, tan of tan x. And then the last thing is the derivative of the inside, which is the tangent x, which is secant squared x. All right, so last one, number 4. Derivative of y with respect to x. Remember, whenever it's e, it's going to stay exactly the same. And then we just need to follow that up with the derivative of the exponent, which in this case is negative 7. Okay, today we're doing more L'Hopital's rule. So we're going to start with the definition here at the top. It says L'Hopital's rule applies to the indeterminate form infinity over infinity as well as 0 over 0. Okay, so we now have 2 forms that we are allowed to use L'Hopital's, 0 over 0, and now we also can use infinity over infinity, which is great. Gives us way more options. And then here it just says f and g can be going to positive or negative infinity. So it doesn't have to be positive infinity. All right, so let's look at some examples. Number 1a. So the first thing we want to do is just plug in the the pi over 2 and see what we got. So we have secant of pi over 2, and then we have 1 plus tangent of pi over 2. So if you remember, secant and tangent have asymptotes, right? And they both have asymptotes at pi over 2. So if I was drawing that graph, pi over 2, I have a vertical asymptote there. And so what happens is, like the tan graph, the graph goes up at that point, okay? Secant, I'll draw it in orange, same thing, the graph goes up at that point, okay? So both of them at pi over 2, the limit is is infinity. Okay, if you plugged it in your calculator, you'd get error or undefined or something like that. But the limit is actually infinity. So this gives us infinity, and then 1 plus infinity is just infinity. Okay, so this is now included in our L'Hopital's rule. We are allowed to use L'Hopital's rule on infinity over infinity. So we're going to do that. So we have limit as x approaches pi over 2. So we're going to do the derivative of secant, which is secant tan. And then on the bottom, we have derivative of 1 plus tan x. The 1 gives us nothing. The tangent gives us secant squared. And this cancels one of the secants. Okay, so now I have limit as x goes to pi over 2 of tan x over secant x. Okay, so it would be smart of us at this point to think about what this reduces to, because remember, both tangent and secant are forms of sine and cosine. So let's rewrite it. Okay, we have limit as x approaches pi over 2. Tangent is sine over cosine. Secant is 1 over cosine. Okay, so since secant is on the denominator, if I bring secant to the numerator, 1 over cosine is going to become cosine over 1. And then at that point, my cosines are canceled, and I just have sine. And the sine of pi over 2 is 1. So the answer on this one is 1. All right, I'm going to erase it, so go ahead and pause it if you're still writing. All right, number B. All right, so we're going to plug in infinity. So we have natural log of infinity, and then 2 radical infinity. Okay, so on the top, we have natural log of infinity. Remember what natural log actually is. So it means e to some power equals infinity, and I want to know what power would give me that. And that's going to be infinity. On the bottom, we have 2 radical infinity, which is still just infinity, even though we're doing the square root. All right, so we're going to do L'Hopital's rule because we do have our indeterminate form infinity over infinity. And so we're going to go ahead and do the derivative of the top, derivative of the bottom, and see where that gets us. So we have derivative of the top, 1 over x. Derivative of the bottom, remember it's 2x to the 1/2, so that becomes x to the negative 1/2. All right, so at this point, it would actually be helpful if we took the time to kind of reduce this a little bit, okay? So on the top, we have x to the negative 1. On the bottom, we have x to the negative 1/2. Since they are dividing as exponents, they subtract. So let's do that. So I have negative 1 minus a negative 1/2. That's a negative 1/2. Okay, another way of writing that would be 1 over radical x. And so at this point, I'm going to have 1 over infinity. So think about a cookie. I have 1 cookie. I'm cutting it into an infinite amount of pieces. The size of all of those pieces is essentially 0. 1 over infinity equals 0. All right, let's go to C. Okay, on C, we're going to plug in our infinity. So we have e to the infinity over infinity squared. That's just infinity over infinity. So now we have our form, our indeterminate form that we can use L'Hopital's rule. So let's do that. So we have limit as x approaches infinity. The derivative of e to the x is e to the x. The derivative of x squared is 2x. Okay, at this point, we again, when we plug in infinity, are going to have e to the infinity over 2 times infinity. That's infinity over infinity. So we're going to do L'Hopital's rule again. Okay, so we're doing the derivative again. Still going to be e to the x on the top. The bottom, we're going to get 2. Now when I plug in infinity, I just get infinity over 2, which is infinity. All right, next we turn our attention to the indeterminate forms infinity times 0, infinity minus infinity. Sometimes you can convert these forms to a 0 over 0 or infinity over infinity form. Okay, so on these, really important that we're not writing down answers, because even though we might think that infinity times 0 equals 0, it might not. It might not. Or infinity minus infinity, it's not necessarily 0, okay? So what I'm about to show you is some strategies to help you basically manipulate these equations so that they become a form that we can either figure out the answer or use L'Hopital's rule. All right, so let's look at A. On A, we have plugging in the infinity. Infinity times sine of 1 over infinity. Okay, remember, 1 over infinity is 0. So this is infinity times sine of 0, infinity times 0. Okay, that's an indeterminate form. We don't know the answer. So we are going to try to manipulate this so that it's not in that form. Okay, so we're going back a ways. I don't know if you guys remember this, but we're going to use the fact that 1 over infinity equals 0 and 1 over 0 equals infinity, okay? So what we're about to do is instead of going to infinity, we're going to go to 0 plus, and that makes x the reciprocal, 1 over x, sine instead of 1 over x, just x. Okay, and now this is our rule that we love so much. Sine x over x, when we go to 0, that equals 1. Okay, so kind of a surprise on this one. Infinity times 0, we end up with 1. Okay, so this is a good lesson of why we can't assume we know what the answer is going to be when we have these indeterminate forms. All right, let's try B. So on B, we have radical 0 and then natural log of 0. Well, the natural log of 0 is infinity. So this gives me 0 times infinity, and I cannot evaluate that. So on this one, the trick that I'm going to use is I'm actually going to rewrite radical x. I'm going to write it in the denominator as 1 over radical x. Okay, so basically I made it a fraction, I put it in the denominator. If I were to do a drop change flip, this would just be a radical x, just like the original problem, okay? The reason that I did this, and I wrote it like this, is now when I think about infinity, on the top I'm going to get infinity, natural log of 0. On the bottom, I'm going to get 1 over 0, which is also infinity. This is infinity over infinity, which means I can use L'Hopital's rule. Okay, so now I'm going to do my derivative of my top, 1 over x. On the bottom, let's think of it as x to the negative half. So I'm going to get negative 1/2 x to the negative 3/2. Okay. We're going to spend a little bit of time simplifying this down, okay? So I'm running out of room. I'm just going to squeeze this in here. This is x to the negative 1. This is negative 1/2 x to the negative 3/2. If I were to subtract those, because they're dividing, negative 1 minus negative 3/2, I get a positive 1/2, okay? Also, a negative 1/2 on the bottom is a negative 2 on the top. So this gives me negative 2 radical x. Now when I plug in my 0, I get negative 2 times 0, which is 0. Okay, number 3. On this one, I get 1 over 0 when I plug in the 0 minus 1 over 0. That's infinity minus infinity. Okay, remember, we're not allowed to just assume, oh, that's going to be 0. We don't know. So we want to try to do something here to make this maybe into a form where I can use L'Hopital's rule. Okay, so one thing I'm noticing is I have two fractions. What if I got a common denominator? We can try. All right, so if I do that, limit as x approaches 0, I would have x minus sine x over x sine x. And that's just getting a common denominator. All right, so now if I were to plug in the 0, on the top I would have 0 minus 0. On the bottom I would have 0 times 0. 0 over 0, I can use L'Hopital's. All right, so here we go. On the top, my derivative, I get 1 minus cosine of x. In my denominator, I do have to use product rule. So I'm going to have derivative of the first, which is 1, times the second, plus derivative of the second, which is cosine x, times the first. All right, now let's try plugging in the 0. On the top, I'm going to have 1 minus cosine of 0 is 1. On the bottom, I'm going to have 0 plus 0 times 1. So this is still going to be 0 over 0. I'm going to go ahead and do L'Hopital's rule again. I'm going to erase what I just did, so if you still need it, pause it. Okay, this is going to allow me to go down here now. Okay, maybe I'll just do this over here. 1 minus 1, 0 plus 0. Okay. All right, on the bottom now, I'm going to do my derivative again. So on the top, I get sine x. On the bottom, I get cosine x plus, and now I do need to do product rule for my x cosine x. So derivative of the first times the second, plus derivative of the second, that's going to be a negative, x sine x times the first. Okay. All right, so now let's try plugging in our 0. On the top, I'm going to get sine of 0, which is 0. On the bottom, I'm going to get 1 plus 1 minus 0. Well, guess what? 0 over 2, that's perfectly fine. The answer is 0. All right, last thing today, last thing for the week. Limits that lead to the indeterminate forms 1 to the infinity, 0 to the 0, or infinity to the 0 can sometimes be handled by first taking the logarithm of the function. We use L'Hopital's rule to find the limit of the logarithmic expression, and then we exponentiate the result to find the original function limit. Okay, so this is basically trickery and deceit. We're going to pull a fast one, and then at the end, we'll just undo it. All right, we have a little bit explanation here. What they're basically doing is they're taking the natural log of the function. They're able to do the limit of that, and then to undo that at the end, you take whatever you got for the limit, and you do e to that number. And that undoes the natural log that you did in the beginning. Because we can't just do something to a function. We have to at some point undo it, okay? All right, let me show you. So let's look at number 4. Show that the limit as x approaches 0 positive of 1 plus x to the 1 over x equals e. Okay, so first, let's just take a look at this real quick, this function here. We're plugging in 0, so we have 1 plus 0 to the 1 over 0. 1 plus 0 is 1. 1 over 0 is infinity. Okay, 1 to the infinity, that's indeterminate. It does not necessarily equal 1, okay? So we are not allowed to just evaluate that. So we're going to use this little trick that I told you guys about. First thing we're going to do, we're going to take this function, the original function, and we're going to go ahead and do the natural log of it. Okay. The reason that's a good idea is because what we can now do is we can take this exponent, we can bring it down front. Okay, so now let's look at our limit. Okay, so we have limit as x approaches 0 plus of 1 over x, natural log of 1 plus x. The reason why this is good is because now when we go ahead and evaluate this at 0, we have 1 over 0 times the natural log of 1, which is 0. Well, this is just 0 over 0. So that means I can use L'Hopital's rule. Okay. So this is my top. This is my bottom. Okay, so we have derivative of the top. That's going to be 1 over 1 plus x. On the bottom, I just have the x. That's going to be 1. Now let's go ahead and plug in our 0. 1 over 1 plus 0 over 1. So that's going to be 1 over 1 over 1. So everything is just 1. All right, easy enough. Now, don't forget, at one point in this problem, we did the natural log of this function, okay? So our answer is not going to be 1 because we did something that now we have to undo, okay? So when you take the natural log of something, to undo that, you do e to that power. So since we got an answer of 1, our limit is actually going to be e to the 1, which is just e. And that's what we were trying to prove. All right, let's try another one. Same sort of thing. I'm going to show you guys one more time how that works. Okay, so first thing we want to do is look at this one. This one's going to be infinity to the 1 over infinity. Okay, I'm plugging in the infinity for the x. That's infinity to the 0. Don't know that. Indeterminate. Okay, so what I'm going to do first, I'm going to do the natural log of this. This is the original function, natural log of x to the 1 over x. That is a good idea because it allows me to take my exponent, bring it down front. So I have 1 over x, natural log of x. All right, now we're going to do our limit. X approaches infinity. Why don't I write this as the x on the bottom? Okay, so same thing as what I just wrote. The x is the bottom of the fraction. All right, now when I plug in infinity, I have natural log of infinity, which is infinity, over infinity. That's a form that I'm allowed to use L'Hopital's. Okay, so I'm going to do the derivative of the top. 1 over x, derivative of the bottom is 1. So now I have 1 over infinity, which is 0 over 1, which is 0. Okay, that's good. Remember, we did a little bit of trickery here. We did our natural log. We got to undo that. So, see how I got 0? My final answer is going to be e to the 0, which is 1. That is my final answer. All right, I hope this made a little bit of sense to you guys. You are going to go ahead and try your homework 3.8, and I will be getting with you guys soon to go over everything.